Okay, so this lecture is meant to introduce you guys to the idea of compound circuits. And so far we've just looked at circuits where you had resistors that were just in series or just in parallel. And now we're going to look at more realistic cases where you have resistors that are in both series and in parallel, and you have these kind of combinations. So before we kind of tackle what's happening with current and voltage, we're just going to look at what's happening in terms of resistance to our system. So I'm going to give you a little bit of a strategy in terms of how do you effectively reduce the circuit down to one resistor. And so this kind of section is compound circuits, but this is going to be called finding the total or the equivalent resistance. And the first thing that you're going to do when finding the total resistance is you are going to combine the resistors that are furthest away from the battery or that are in like a separate system, I guess I could kind of say. So you're going to start by isolating pairs or combinations of resistors. And combine them to an equivalent resistance. And then you just kind of keep on going. You keep combining pairs or combos of resistors and finding the equivalent resistance. So continue with this until you have reduced the circuit down to one resistor. So you've taken all these resistors and you've kind of collapsed it down to one resistor. So continue with this until the circuit has one resistor. And that one resistor then is equivalent to the total resistance present in the circuit. So I know that this kind of seems abstract, and so I want to go through a couple of examples with you in looking at isolating a combination of resistors, combining them, and then repeating. Okay. So this first situation, I have 4 resistors, and you may want to pause the video so that you can actually draw this out in your notes, because I'm just going to go right into it. So the steps said that start with the combination or the pair of resistors, and so realistically these two are combined in parallel with each other. So what you would do is you would combine these 2 resistors. So you have a 2 ohm and a 6 ohm resistor, and they're connected in parallel. And we've seen that resistors in parallel combine as inverses of each other. So like this parallel combination, if I were to say 1 over R parallel, it would be 1 over 2 plus 1 over 6. And so you know how to calculate this in your calculator. We've done this already. We would do 2 inverse plus 6 inverse equal inverse that. And you would find out that this combination of this 2 and this 6 in parallel is equivalent to a 1.5 ohm resistor. So what that means when I say it's equivalent is I could have an almost identical circuit with a 7 ohm and a 3 ohm resistor, and then right here in this kind of like region, this parallel combination is the same thing as having a 1.5 ohm resistor. Like these are equivalent circuits. And so now at this point, we're going to keep on going. We're going to collapse the circuit. We're going to reduce this. Well, these are just 3 resistors in one path. And whenever you have resistors in one path, that's a series circuit. And so we know that this would just, if I were to find the total, resistors in series just add up. So it would be 7 plus 3 plus 1.5, and that would be a total resistance of 11.5 ohms. Okay. So this is a pretty simple example of reducing the circuit down to one resistor. So let's try another one. So again, you may want to pause the video and draw this out in your notes. I do, when I'm going to go check your online lecture notes tomorrow, I am expecting to see that you've drawn these circuits out and you have gone through the process of reducing the circuit. You're not just listening to me talk. So in this situation, I've got a whole bunch of resistors. And again, we want to kind of start with the most complicated pairing or combination of resistors. And so the first thing that should really jump out at you is this parallel situation. So if I were to combine this 6 and this 2 in parallel, remember 6 and 2 in parallel, they're going to combine as inverses. So it'll be 1 over 6 plus 1 over 2. And we know how to do that. We actually just did an example with a 6 and a 2. And that means that this is going to become 1.5 ohms. And so we could actually redraw the circuit. So I'm going to redraw it real quickly. There's my 6 ohm. There's my 4 ohm. And this piece right here, this is the same as having a 1.5 ohm resistor. And then I still have this 2.5 ohm resistor. Okay. And so now again, I need to reduce the circuit again. Now, before I can combine this 4 with like this 2.5 or this 4 with this 1.5, these two resistors are connected in series first. So this combination is connected in series, and then that is connected in parallel. So I need to combine these guys. And this is one path, and so one path means that they're connected in series, and we know resistors in series, they're just going to add up. So 1.5 plus 2.5, that is 4. So again, I could redraw my circuit, and you probably can make this a little neater in your notes, but I'm kind of running out of space. So I've got my 6 ohm, my 4 ohms, and then this other path has 4 ohms. So again, I have these guys in parallel with each other, and resistors in parallel are going to add up as inverses. And another just kind of like little trick is that whenever you have two resistors that are identical and they are in parallel with each other, they are just going to, like the equivalent resistance is just equal to half of one of the resistors. Just when you do the math, 1/4 plus 1/4 is 1/2. Flip it, that's 2. So then your next circuit would look like this, where this is 6 ohms, this is 2 ohms, and again, look, you have a single path, and when it's a single path, they're resistors in series, and they would just add. So the equivalent resistance of this circuit, or the total resistance, is just 8 ohms. So this entire circuit behaves as if it would be equivalent. It would behave just the same way in terms of how much current gets to come out of the power supply as if there was just one single 8 ohm resistor. Okay, that's the whole idea of equivalent resistance or total resistance. Like, what does this behave similarly to? Now, in terms of like, well, why does that matter? That helps determine how much current is coming out of the power supply. And the amount of current that comes out of the power supply is going to kind of drive the rest of our system. So let's go ahead and look at one last example where we find the total resistance, but then we take that next step and we find the total current as well. Okay? So again, this one's a bit more complicated, just to see if you can do this. So I would recommend pausing the video and drawing this out. And I would actually recommend, like, if you're up for the challenge, to pause the video, draw this out, see if you can do this on your own, and then play the video and see if what you're doing is what I'm doing as well. Okay, so again, you can make that choice. I'd highly recommend it. It would just give you good practice, but I'm not there sitting on your shoulder telling you what to do. So as we go to tackle this, you can actually do 2 steps in one, because you can see, oh, I've got a parallel combination here, I've got a parallel combination here. So you could say, hey, what is this combo of resistors in parallel, and what is this combo of resistors in parallel? So this would be 5 inverse plus 2 inverse, then inverse that total, 5 inverse plus 6 inverse, then inverse that total. So again, I'd recommend you try to calculate that out. I am going to redraw the circuit, and I got to redraw it here because I don't have any space. So I have my 3 ohm resistor. This reduces down to a single value, and I calculate out that it comes out to be 1.43 ohms. And then I have this 4 ohm. And then this reduces down, if I inverse 5 plus inverse 6, and then inverse that total, I calculate that out to be 2.73 ohms. And then this is 1.5 ohms. So now you can see this is just one big path. And so if it's one big path, these are all in series with each other. And we know resistors in series just add up. So we could easily just say 3 plus 1.43 plus 4 plus 2.73 plus 1.5, and they're going to give me a total resistance value of 12.66 ohms. Now, in terms of like solving the problem, the first part says to find the R total, and then the second part says find the total current coming out of the power supply. Well, we have this equation called Ohm's law, and Ohm's law says that I is equal to V over R, but I'm going to add some subscripts. So this equation applies to all situations, but the subscripts have to agree. So if I'm trying to find the total current, then I got to make sure I'm using the total voltage, and I got to make sure I'm using the total resistance. So I know in my problem that I've got a 12-volt battery, so this is going to be 12 over my total resistance of 12.66, and that is going to give me a little less than 1. 0.95 amps. Okay. So that's just how you would reduce the circuit to find the total resistance of the situation. And then we're going to use that to figure out what the total current is. So at this point, you guys are going to get a glue-in from the sub, and you're going to work on that glue-in for a little bit. And when you're done with that glue-in, we'll correct it when you get back to class tomorrow, or when I get back to class tomorrow. And so when you're done with that, you're going to move on to the next part of the lesson for today. There's another online lecture that's just kind of give you some framework before you move on.